talk about transformers. So we found the full load current for the transformer, the short circuit. We did the connection, high voltage, low voltage connection, as well as delta Y. And we say the secret for the delta and the Y, when you do delta, never go one end, you go beginning to end of the core, like X1 to X2. Never go X1 to X1. That's really the tricky one when you do it. Unless you're doing a Y, then you put all the X1s together into the neutral, and the rest of them goes to the other side, either H1s or X1s. Okay, the second thing that we're going to talk about, guys, is buck boost transformers. Equipment, guys, must match. Right? Now, what happens if there's a gap? If the gap up to 20% gap, you can bridge that gap between the voltage, resistance, the voltage, 20%. You can have a buck boost transformer, tiny little dude that can bring the voltage of the equipment up to the voltage of the system. So why? Because equipment want, if they're rated for a certain voltage, they want this voltage. A good example is going from 280 to 240. Remember what happened to the meters that we talked about when it went from 280 to 240, how it added a lot of power on it. It could burn the equipment. Same thing. So we can buck or boost the voltage um, to match it to the system. All what there are, I don't know how many of you guys have figured out. If you're doing maintenance, you probably have figured how many boost transformers, three phase it is. We're only going to be worried about these three connection, buck and boost for the test. What you need to worry about, like I said, I'll show you the connection. I want you guys to look at this wire right here in particular. For all of them, look at this wire coming from here, so all the way. Like keep your eyes on this wire right here. Okay, so this is the wire that if you flip it, you get buck or boost. Start with. These are three systems, bucking or boosting three systems. So let's show you how you buck it by making it additive or subtractive polarity. If you take this wire, now I'm going to buck it. Look what happened. I went from even to even here, and then I pulled my wire from here. If I went this way, this is bucking the system. The voltage will be lower. Okay, so you're going to be lowering the voltage. The same thing, if you came from here to here and you came out from this side, that's bucking the system. Look at this again. You're coming from here to here and come from this side here. Can you guys see that? By you basically boosting the voltage. So what you do is you I want now. So this is 115. I want to remind you guys this is rated for 115. This is rated for 115. What happened when you series two coils? High voltage. Okay, now what if I need lower voltage? So look how we hook them up right here. You took the same coils that they were sitting like this, and you just tied them at the end, right? That's your low voltage. Everybody can see that. This is your low voltage right in here. Okay. Then the same thing, and that's the only difference. So I can take 115 now and boost it up to 126. Well, what we did at the second one, guys, they were high voltage. I flipped them, make them low voltage, series them. Now, what happens if I need at 115, this stays the same. At 115, I need to put 20%. So now remember, this And it looks like this. Look at the box. Box is a book. Exactly the same. The only difference is where the green wire and red wire is connected. Makes sense? Is your box is your boost. Like I said, there's hundreds of connections for different voltages. Don't worry about it for the test anyway. Okay, questions about buck boost? About buck boost. Okay, any comments, gentlemen? Any questions? If you came from the odd side of the primary, you got your boost. If you went from the even, here's what I'm mentioning. If you came from the even side here, you came to the odd side, like connecting them this way, that's boost. If you came from this side to the even side right here, that'll get you a buck. The current is going this way, guys. The voltages add up. If you bring the current this way, it's really no rocket science on that one. Okay, neutral calculation. Any comments, guys, questions about this one before we go to neutral calculation? Neutral calculation. Okay, for neutral calculation, I want to bring to your attention, gentlemen, that this is your voltage. This is the voltage that we're doing calculation about. This is your voltage system. These are the voltage system that we're dealing with. So here's my phase A, here's my neutral, here's my phase B, and here's my phase C. And this is coming out of my a grounded power. You bring a wire here, you ground it. This is called solidly grounded neutral Y. Solidly grounded Y transformer that gets you a solid neutral Y, solid neutral. Solid ground and give you a neutral. Okay. If there is no harmonics and you need to find the current that goes through the neutral, the current that goes through neutral will be a function of all the others. So you square the current in each one of them, and then you multiply each current by the other current, and then subtract them from the sum of the squares. So how are you going to do this one in your calculator? So square current A, current B, current C, square them, add them up, then subtract from them the product of each current by the other current. All right, let's take this. Now remember, now what happens if this is carrying 10 amps and this is carrying 10 amps and this is carrying this is carrying 10 amps and this is carrying 10 amps, how much would the neutral be carrying? Zero. So that's a balanced three-phase system. That's the beauty of the three-phase system. So if all of them are carrying zero and there is no harmonics, remember there's something called harmonics. Zero. If you don't believe Chad, plug on all their numbers and that will get you zero. Now what happened if one phase, they're all the same except one phase is off? What do you think the system would carry? The same amount of current. The same amount of current that the C and the B are carrying. Now this is the most confusing one because you guys get this one confused with this system, right? Here's my neutral here. What happened if I have? We just talked about this one here and this here. What happened if this is 10 amps and this is 10 amps? What would the neutral carry? 0 amps. That's from a single phase system though. Now look how this is going to happen. Now once I add another phase here, okay, and I add a neutral and I put a switch on it, turn it off, and bring it here. See how now this become a three-phase system. Now the answer goes from 0 to what? To 10. Does that make sense? This power system versus solidly grounded Y. That's 10. Now what happens if the two phases are off? So these are in one phase, phase A, phase B, phase C, and you turn this phase and these lights off. This is single phase circuit. What would the neutral carry in a single phase circuit? Same current as a phase. Now, all hell break loose and you get grab your calculator and let's do it together, gentlemen. So here's what you're going to do. You're going to do all this math. First, you need to go. You go 5 times equal. That'll get you 5 plus, and then hit memory plus. Oh, I have to clear memory. If you're like me, guys, make sure your memory is clear before you start this because we used it before. Okay, so 5 times memory plus, and then 6 times memory plus, and then 8 times memory plus. Okay, these are all the memory pluses. Now let's go to memory minus. 5 times 6. 5 times 6 memory minus above it. And 6 times 8 memory minus. And 5 times 8 memory minus. Then recall memory. You guys get 7? If you didn't get 7, then you did something wrong. And then take the square root of it. Gentlemen, all in one step in this archaic calculator. Does that make sense? It comes handy. Okay. Any questions, guys, about neutral before we move to motors? Any questions about neutrals? Okay, now motors. Um, coils, coils, and inside them a chunk of steel. All right, so once you add once you couple this shaft here, and you add to it a machine, a fan or something, or you got yourself a load on this motor, a fan, a conveyor, whatever. You plug in from the shaft. So the shaft is the point of coming coupling between your mechanical loads and electrical loads. Okay, so the power comes from here, gentlemen, get converted inside this machine from electrical power into mechanical power, and the mechanical power comes in the form of rotation. So mechanical energy. Generators do that. The other thing is the engines. They will take chemical energy, convert it into mechanical energy or electrical energy if they're generators. All right. So you create a magnetic field, guys, induce the magnetic field right into the stator, creating a magnetic field. The north and south pull away from each other. South attracts the north, and you get that magic that's called spinning. Induction motor is the least maintenance ones because there's nothing inside it, no wires. There's nothing connected to. Okay, for you guys for the test. Test related, you need to know this formula. The synchronous speed of a motor. The synchronous speed of a motor, gentlemen, is the speed of the magnetic. See that magnetic, the speed of the magnetic field inside the motor. The speed of the magnetic field inside the motor is called the synchronous. It's 120 times the frequency divided by number of poles. So they'll ask you to find the number of poles or the frequency. What happens if you want to flip this formula for a number of poles? What do? You swap what by what? As with number of poles. That's it. Swap them. Okay. Um, so no current rotor, no rotor. Okay. So at synchronous speed, if you run them at synchronous speed, there will be no rotor induced and so forth. Let's go into a slip. Slip. The rotor itself is typically slightly lower behind the synchronous speed by typically 3 to 5, 6% behind it. And that's how you get torque out of the machine. That's called the slip. So you take synchronous divided by actual, get you the slip. Slip percentage is the slip divided by the synchronous speed. That's called the slip percentage. How far is the actual speed of the rotor from the theoretical speed of the magnetic field? So please remember that one too. Okay, so these are the things that you need to know first about motors. Basically, these formulas, this one, and these two. All right, here we go. What is the speed of a 60 horsepower 4-pole motor with a slip of 75 that is connected to a 483 phase system? Now, talk about extenuation information to basically mislead you. Did you guys see any in the formulas that we went over? Is there anything about voltage? Voltage is not a factor. All right, so you need the actual speed. First, you need to find the synchronous speed and then subtract from it the slip, and that will get you the actual speed, right? The difference between actual and synchronous is the slip. So there you go. Here's your formula. Plug it in. I have an 1800 RPM massa, synchronous speed. Subtract 75 RPM from it. They'll give you a 1725. 1725. So remember, the synchronous speed is always more than the actual speed. So if your answer ends up 1875, that's not true. I believe if you have VFDs, you can drive your motor higher than the synchronous speed by manipulating the frequency. Any question, guys, about this calculation? The first thing you need to know about motors. That's among a lot of other things that we need to be doing. Okay, what do you need to know? You need to know how to find the synchronous speed. The actual minus the synchronous. And, okay, can somebody tell me what the 1800, right? So slip percentage right here. So if you need the slip percentage, you take it divided by synchronous speed. So if you take this 75, I don't know what would that give you. 75 divided by 1800 RPM, that'll get you synchronous speed and slip percentage. Slip percentage. Okay, we have another motor that has 1200 RPM. How many poles does this motor have? How many poles does this motor have? So do you guys remember the synchronous speed equal 120 multiplied by the frequency divided by the poles? So now you need the poles. What do you do? What do you swap by what? Swap these two. So this becomes P equal 120 multiplied by frequency divided by what? SS. That's it. So plug them in, and you got yourself 120 multiplied um, 6 poles. So here's one pole. Here's your 2 poles. And I know, just trying to, it will be slightly his 4 pole, and it'll be slightly different because they have to be equally away. So here's your 2 poles, 4 poles, 6 poles. Any comments, guys? Any questions about the poles or finding the poles of the synchronous speed, finding the synchronous speed, finding the poles, actual speed? Okay. For motors, gentlemen, you have to talk about horsepower calculation for motors. So there's 6 things. First thing you need to do is the synchronous speed calculation. A lot of formulas, guys, but focus on getting them. It'll be really, I think it's really easier than monkeying around trying to find a question about the code that will take you forever to find it. So you increase your chances of surviving the test if you know the code. Okay, horse mechanical power to electrical power conversion. How do you convert these? Smarter than Chad. We started with the horsepower in the universe, right? Because we didn't have cars or anything else. So a horsepower is equivalent to 746. So if you need 1 horsepower to run a mechanical machine, efficiency. Remember, yes, right? Machines. Every machine has efficiency issues. There's no 100% efficiency. So, but the conversion factors start right there. Um, Efficiency of the equipment, um, meaning how much power you can get. So let's just take this one here, for example. Suppose this machine is my machine. It's a 10 horsepower machine, and I'm bringing 10 kW. I'm I'm bringing 10 kW to a 10 horsepower machine. 10 horsepower. What's the efficiency of that machine? Piece of cake. You have to convert the horsepower cars into kVA and divide this by 10. 10K. Remember, here's my horsepower divided by 746. And anybody can see that this is actually almost 75%. 75%. This machine is only 75% efficient machine, right? Since it's 10 horsepower, you can't divide watts by horsepower. You have to convert 75% efficient machine. That's my efficiency. Uh, don't don't forget that the power factor is always the true power divided by the pure power. That comes very handy. And then, gentlemen, we get into the formula that we need to use in a second here. Here's the formula that you need to use. Um, I want to remind you guys that this is Ohm's law. Everybody understand that this is Ohm's law? E times I. Okay. Anybody can tell me where does this component came from? Please. All right. Why is the power factor in the equation? Because when it deals with motors, we always deal with true power, not apparent, not reactive. So I need the true power, then I have to multiply by the power factor. Anybody knows what 746 is? That's the conversion between mechanical and electrical power. Every 1 horsepower is equivalent to what? 746. Anybody knows what Miss Efficiency is doing here? Do you expect if you put 10 kW in this motor, mechanically speaking, coupling as it goes through the gear and from another gear to another gear, and that's conversion and run machines and so forth. And the third gear will be here, and you're driving all these gears together, right? That's what they're doing with them. Do you think by the time you're really going to have the 10 kW, will have 10 kW worth of work, or are we going to have losses? Losses. The efficiency is for losses. Okay? This formula you guys must memorize. It's easy to remember. The way I remember it personally is power. To help you with the following. Can anybody tell me what's the only thing that could change if this was single phase? I need you to pinpoint to one thing that will change. If that was single phase, what's the only thing that would change? Done. Perfect. Same equation. Okay, second thing. I would like you guys to pinpoint me to the two things that will change if that was a DC motor. But one of them is already crossed, right? That's crossed because DC doesn't have 1.7D. Does the DC have power factor? No, the power factor. Gentlemen, here's the formula for DC. All motors. So memorize this. See that? Here's one for the DC. Can you see that? DC formula is AC formula single phase. But we don't need. Any comments, guys? Does that make sense? No, yes? Okay. Let me do one thing about that. Do it this way. Let me ask you on the test, guys. They might ask you. Let's just do. How about if they ask about the current? Let's solve this equation for a current. Do you guys remember that formula? So I'm going to go drop the horsepower right here. Is my horsepower equal? Is here. Drop the equal. And then the one that I need, they want me to find. What do I do with it? I drop it on this side. That's your starting point. Anybody knows what's next? Remember that rule, what's at the top goes at the bottom, what's at the bottom goes at the top. So all this junk at the top, you can see that, where would it go? Bottom of the other side. Okay. I could write them up there, but I just write them at the bottom because it's easier. So that would be 1.732 times E times Miss F. Are we done? No. What's next? Next is to get the bottom. What's at the bottom? At the bottom is this. So this has to be swung all the way and come to where? To the top. So that will be 746. And you're done. That's how you find multiplying by the reciprocals. Okay, now we flip the formula. Don't let it bother you guys. What is the horsepower of 480 three-phase point power factor? Everything is given. You have the voltage, you have the efficiency, you have the power factor, and you have the amp, and they're telling you, can you please find the horsepower? I can't find it. Is it three phase or single phase? Three phase. So don't forget the 1.732. They don't make 14.98, guys. You are stuck with the next standard up, which is 15. 15. Any comments, guys, questions about that? Make sense? Look at the other one. Line current. Okay, so you want to have they want the line current. It's a 3 horsepower. It's a single phase. What happened to 1.732? Out the window. Is the power factor. The efficiency is power factor. So remember that how we flipped it to find the current? 1.732. Uh, eighth grade math. Remember that? Like this. How do you do this with you? called memory. Any comments, questions, guys? On the test. Makes more sense in the most part. Connections. How are you guys doing with the connection? Motor connections? Um, for connection, guys, there are two types of motors. There's for single phase. Well, there are multiple types of motors. For the test, you guys need two. There's single phase and three phase. Single phase motors, guys, come always labeled T1, T2, and 3 and 4, and 5 and 8. 5 and 8. That's it. Do you guys remember how we make low voltage? What do you do when you have coils? You make low voltage. You parallel them. To make high voltage, what do you do? Series them. In order to get a low voltage, what do you need to do? All the odds together, all the even together, and then you go to hot 1, hot 2. That will get you low voltage. All right, what's a low voltage? If this motor has two voltages, 120 and 240, you tie all the odds together, all the evens together, get you high voltage, low voltage. I want to warn you guys that here's how to give you the connection. Is this a wrong connection? All the even together, except 5 and 8 are split. What is that right connection? Yeah, what's wrong with what's special about it? You're reversing the rotation. So if they tell you counterclockwise, low voltage counterclockwise, clockwise is what you're looking at. Counterclockwise, if you flip 5 and 8. You flip 5 and 8. Both of them are right, except if they're asking if you put the centrifugal, see, where's my centrifugal switch right here? See, these guys must be in this right there. The centrifugal switch and start capacitor. Nothing torque. Oh, just to start. It's not needed. It just starting winding. Any comments, guys, about the starting winding? You understand the connection? All right, high voltage. High voltage. Um, so what happened is 2 goes to 3, and they go to 5. So go 2, 3, and 5 go together right here. That will get you low voltage. Now, what's wrong with bringing 5 all the way to here? Anybody? In series. So T1, T2, T3, T4, 1 and 4 go to 1. One. So you're looking at clockwise. If I want counterclockwise, I can make this is 8 and this is 5. This is counterclockwise. This is clockwise. Any comments, guys? Questions? Grab these two. Which is always with the starting, not the running coil. Okay, on the test, what did you do? High voltage. Any comments, guys? I always tell the people, guys. All right, let's go 3 phase. How are you guys doing with a 3 phase? Good, bad, or ugly? For 3 phase motors, um, if your motor is a delta here, delta, let's just say delta 480, 480 delta. What's the voltage across the coil? 480, right? Know how much torque that guy can kick at 480 a coil? Now, the same thing, what happens if you put the voltage here, at 480 voltage, right here? What's the voltage across the coil? 277. That's almost half of that. So which one do you think is going to have more torque, starting torque? The delta motor. They have more starting torque because they have more voltage across, even though for the same voltage, more voltage across the coil because that's what matters. You know. By the way, if you want more torque, delta motors will get you more torque. Or one solution. So let's go labeling, guys. The single most important thing about delta is labeling them. Here's the convention for labeling. Not sure about you guys. A lot of people memorize things, but I like to understand it. So you start labeling. It's very easy, the first one. 1, 2, 3. How hard would that be? And you have to draw a star because Y motors comes with a star, and on top of each star there is a coil with two wires, a coil with two ends. Can you guys see that? That's a coil with two ends. That's how Y comes. A star right on the top of it. Okay. Now once you reach 3, then you have to avoid being anywhere in this line. So you're in phase 3. Okay. You have to go all the way to you're jumping from phase to phase and going spiral. That's the key point. Jump from phase to phase. You can't stay in the same phase twice in a row. You have to keep jumping and going spiral. So this will be 3. Do you think I can make this 4? This means I'm staying in the same phase. No, I have to jump. Remember, we're jumping. This will make it 4. How about here? Can I make this 5? No, I have to jump and make this 5. Can I make this a 6 here? Then this means I'm staying on the same phase. I have to, you label, you jump, and you keep going spiral. So that will make this one 6, and then now I have no option. 6. Am I off? 1, 2. Oh, thank you. 3. This is 4. Oh, that sounds 4. Thank you. And this is 5. It sounds weird. 5. This is 6. Thank you. And this is 7. Now we're right. This is 8. And this is 9. Does that make sense? Once you label them, gentlemen, then it's piece of cake. How do you make high voltage out of two coils? What do you do with them? Can you give me the word? Series them. So you tie these two ends together. And where do you bring phase A, phase B, and phase C, gentlemen? 1, 2, 3. This is L1, L3, and L2. Okay. Any question, guys, about having a high voltage? Look at the Y. Look at the Y. What does that mean? Let's go get another color. So tie these ends. Can you guys see that? Everybody can see that we made another star. And then what do you need to do? Tie the ends of each one, parallel them basically. And gentlemen, and don't forget that L1 goes here, L2 goes here, and L3 goes here. high voltage and low voltage delta. High voltage and low voltage Y, I mean. These and they say pick the right connection. That's how you do it. Pick the right, you can draw them and pick the right one that gives you a high voltage or low voltage. I want to remind you guys that these can interchange. What happens if you flip L1 and L2? Yeah, opposite direction. Clockwise. Once one of them, where are you going? Any comments or questions about that? The Y, high voltage, low voltage? Let's go to the delta. Deltas, guys, are they come in four pieces. This is how I remember delta. The manufacturer they come in three pieces, like corners, like these. That's how they come from the manufacturer. Each one has three leads. Can you guys see that? Three leads that you need to hook up. Okay, so three leads. How do you know which one? Great. How do you identify them if you don't know they are? My God, there's a whole method of identifying a wire delta. Okay, map, spin them, see what the rotation is going, and a whole different story. If you don't know which one is one, two, three to identify them. Okay, now labeling. Here's what we're going to be following, guys, right here. Following that rule. Okay, you start from the top and you call this is 1, 2, and 3. Okay, now you shall not stay on the same side. So I'm at 3 here. Can I call this is 4 or this 4? I have to jump all the way to the other end. So this will make it 4. I can't make this is 5. This has to be 5. I can't make this is 6. This has to be 6. This has to be 7. And this has to be 8. And this has to be 9. Now, once you connect them, guys, once you connect them, you identify them, then you can connect them. If you time together like this, you get yourself high voltage. How do you get a low voltage? Well, how about if we take, you see where 4 is? Right here. How about if we take 4 all the way to where? 2. What else? If we take 7 all the way to 1. And where does the 5 go? 5 go to 3. And 8 goes to 2. And 9 goes to 3. And 6 goes all the way to 1. Coil high voltage, cut off the coil, low voltage. from one end to the other, and you keep jumping between the phases. On the test, gentlemen, on the test, they will get you a three-phase motor like this. Okay, which one is high voltage? Pick out of these five the one that's high voltage. Um, Reminder. Counterclockwise motor. Any questions, guys, about motor? Okay, 5 minutes, guys. Quick here. Okay, gentlemen. Control circuits. Good thing, guys, is they wouldn't ask you what to do. They wouldn't ask you about connecting DSP or soft start. Not like there's a whole lot of connection now. Just plug and play on the numbers. But the single fundamental controller is the magnet, so-called the magnetic controller. You have to- That's the magnetic contactor. Okay, so what do you need to know about that? I want you guys to pay attention to how this is drawn. See that little thing at the bottom? It must be like this. This is the start. The stop. Look where the stop start. How it's the stop is. We draw the stop. Look at the coil. Coil. The holding contact must always go across the start, not the stop. Um, the overload must always be in the side where the neutral is, if there's a neutral. If there's a neutral, the neutral, you have to put the overload on the side where the neutral is. Anybody knows why we do that? Because if you put it on the other side and you have a ground fault, you start your motor even when the overload is open. You start your motor even even when the overload is open. So that's basically the fundamental understanding here. How does that work? You push this one, you closes. Once this closed, this energized. Now this shuts the contacts. Now the current is coming from here. It cooks the coil, and out it goes back. That's your circuit. Once the coil is cooked, then it will send, there's plungers that it drives to drive multiple contacts, separate contacts in a separate circuit to the side. And these contacts are coming to a motor, and bam, 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 my motor is running. Once you push the stop button, it stops the whole mechanism. Any comments, guys, questions about the magnetic contactor? What's in it for you? On the test, they'll give you a couple of diagrams and say which connection is the right connection for starting, stopping, sometimes jogging, sometimes reversing a three-phase motor. So they either ask about start, stop, reverse, or jog. So this is start, stop. Now, you guys remember the three-way switches that we do so you can turn things on and off, three and four-way switches? You put them to turn things on and off if you're using a high voltage switches. If you're using a low voltage switches, do you need them? No. Low voltage switches drive a magnetic contactor, drive a power pack, which is a relay basically. You can have 100 low voltage switches driving the same contact um, in a power pack. Okay, for this one, guys, you must always series the stops and you shall always parallel the start. That's a rule. Series the stop, parallel the start. And the holding contact must always be across what? The start. Any comments, guys? Any questions? Comments, questions about that? Do I always need a fuse here? Do I always need a fuse? Not always. There's later on, guys, I think tomorrow, we'll talk about when do you need a fuse in a control circuit and when you don't need a fuse. You can, the question is, are you required to have a fuse? You can put fuse anytime. Are you required to have a fuse? Certain application, yes. Actually, depending on, as long as we are, depending on the size of the wire here. Say if that was 12, and depending on the overcompression device ahead of it, and I can't recall now how much it allows you, you can either need a fuse or you don't. Now remember, this is a control circuit, so I can go as low as what? 18. As low as 18 gauge. It's a control circuit. Okay, now how do you reverse a three-phase motor? You have two magnetic contactors. You wire them as shown. So you have a circuit. Here's my forward magnetic contactor. Here's my reverse magnetic contactor. Can you guys see that? Then you have, and then here's what you have, gentlemen. You have, can you guys see the overload must be at the end so you can overload them and stop them and start them from starting mechanism. You stop the motor either way. And you the other tricky one is when you reverse a three-phase motor, guys, we flip two phases. Okay, so we need so-called electrical interlocking. Can you guys see that? In the forward control circuit, you cannot go reverse while it's going forward. Together. So what mechanical interlocking happen on the handle here between this handle as you push it and this handle. They will be mechanically coupled together where one goes up, the other one go down. And sometimes they have off. You will have some of them have forward, forward. You push the forward and you open the reverse. Reverse opens whatever the reverse will go forward and the forward will go reverse. Okay, the last thing is let's go forward. Suppose that we're going for the reverse. Let's go reverse. So now you push the button here. Now the power came from, let's use a different mechanism here. So the power comes from here, in here, through the stop, right in here. We're going reverse. It comes down here, and you push the button, right? So it's going to go cook that. Now it's cooking it. Now it's coming over here. Stops. Is there any overload condition? No. It continues, and it goes all the way back to the source. That's how you complete the circuit. Now, once this energized, then this will close, and the power will diverge into this side. Now, what happened down here? Down here, gentlemen, we're going reverse. These guys will close. 1, 2, 3. And now I am taking phase. Can you guys look at phase L1 is feeding, is switching with L3. And L3 is switching with L1. And L2 stays the same. That's it. Any comments, guys, questions about forwarding and reversing a three-phase motor? Forwarding and reversing a three-phase motor. Jogging a motor. What does jogging mean? Stadiums, guys, and halls, the wall. I'm sure a lot of them in high schools. Jogging a wall, basically. Conveyors is a good example of jogging. You push the button, you stop some. Um, and the difference between jogging and jogging, you have to have mechanical. Once you remove the you button, it stops. You're just jogging it. Um, contact, you push it, and it runs forever. All of them are momentary. So the first thing you need to do is, since it have a bypass, then you have to bypass the stop button. Can you guys see? This is really the key one right here. So that's how you bypass it. This is your mechanism for bypassing the start, right? The only way you can. Now, if I want to jog this motor, I will push this jogging mechanism down, hold it in this position. I bypass the start station, and my motor is the power is coming, of course, from always from L1 or L2, but in L1, going through the whole mechanism. It cooks the coil, burning the coil. Do I have any overload situation? If there is, this will open. Nothing will start. If nothing, no overload condition, it continues. The current continues to go back all the way, and that's how you drive. Now I can drive these shut. Once you remove your finger off that jogging station, everything stops. Now the starting mechanism is completely slightly different, of course. The starting, you push the button here. Now the current is coming from the same direction in here, in all the way cook it. It goes all the way back. And now to continue cooking it, this will close and bypass the momentary station, start station button. Does that make sense, guys? But the start between normal start, stop, and a jog. So, all right. Here's what they give you in the test. Which jog motor control circuit? Which one is the proper jog motor control circuit? What's wrong with A? Anybody can see what's wrong with A? First, look at the way we drew the stop. Second, don't you think I need a bypass for the start right here? Okay, so A is wrong. What's wrong with B? Okay, how about if I come from right here? No bypass. What's wrong with C? Look at that. Normally closed holding contacts. Since when you get familiar with normal closed, normally open, right? No, holding contacts are normally open contacts, not normally closed. Overloads are normally closed. And then, of course, the last one is you want to focus on getting yourself a bypass. Is my bypass right in here? Uh, no? Is that the bypass? Yes or no? Yeah, that's a bypass. Now, the normal stop would be right next to it, of course. So that's where you go normally. Current comes in here, goes through, get cooked. Now, under normal condition, then this will close and it goes through here. That's the normal operation. And jogging, it will work as long as you're on the start. Only a devil will think of a concept like this. Mhm. By accident, though, that will burn your motor start. Well, the overload will take care of it, though. Okay, so let's go work on that there. When you size, I think okay. Now we're going to switch gear into continuous and non-continuous loads. Is this load continuous? If that's continuous, not continuous. Bonding. Here's what you need to know about Ampicity. Number one, suppose based on continuous and or non-continuous, I came up with one knot. Then I did my derating based on temperature, and I came up with two odd. These are complete separate calculations, have nothing to do with each other. Okay? And then the third separate calculation is voltage drop, and I came up with four odd. Which conductor should I use for this service? The largest. Does that make sense? Three separate unique calculations. On the test, guys, they don't give you the three at the same time. They give you two though. They give you derating and bundling and continuous load. So what do? Calculate based on continuous load, put it aside. Calculate based on derating and temperature, put it aside. Choose the largest of the two, and you're done. You don't double derate. You do not double derate. You don't derate, or no, you don't increase because of continuous, and above it increase also because of what? Of temperature. You treat them completely separate things. Am I making sense? This is the most common confusing one for people. They clarify a lot in 2014. It used to be even more confusing. In 2014 made it very clear. Okay, so then we're going to size branch circuit and services. We're going to do dryer calculation and ranges, gentlemen. But let's talk about, and then after that, we will talk about conduit fill, wire and auxiliary gutters, cable tray sizing, boxes, box fill for 6 or smaller, 4 or larger, motor calculation, neutral, and we end up with grounding. So I typically stop closer to the motor calculation right here, guys. So, and the rest we'll do them tomorrow. So, as we move forward. Okay. Let's go ahead and talk about branch circuit calculation, gentlemen. Branch circuit calculation. Sizing conductors. Um, Branch circuit shall have an ampicity not less than the maximum load. If it's continuous, it has to be 125, like we said. Should protect by overcome protection device. Okay. Um, so we'll take, guys, of a couple of things. The conductor size. So the rule is, here's the rule. The rule is, here's my machine. Here's my overcome protection device for my machine. This is a 10 amp. If this conductor is, if the load is non-continuous, all what you have to do is put 10 amps worth of cable here and 10 amps worth of breaker or fuse here. You're done. Now once this is non-continuous. Once this becomes continuous, let me grab another highlighter. Once it becomes continuous, then here's what you do. You multiply by 1.25. This becomes 12 and a half, right? 12 and a half, and this also becomes what? 12 and a half for the same load if that was continuous. Can you just see that? Continuous load, non-continuous calculation. Motors are assumed from the get-go are continuous. Electric heaters are assumed to be continuous because of their function by the code. Generators, guys, this is confusing. This is between the generator and the overcome protection device. So here's my fuse disconnect on the gen. From the windings here into here, they allow you to size it based on 1.15. But from the breaker on the gen all the way to your service, that's where you bring your service to auto transfer switch. This will be continuous load, 1.25. Making sense? That's a factory wiring side. Yeah. Well, sometimes we also put the generator in bigger building, put the generator here, and we put the breaker on a wall. That, and then you are allowed you to go 15. Capacitors. Now capacitors are nasty, ugly creature. What they do not 25 example for you guys. We talked about continuous loads, guys, and then we shall perform three calculations. Aside, bundling, put it aside. Voltage drop, put it aside. Now you're looking at three calculations from in the three separate calculations to the largest. All right, gentlemen. It is, so 310 of 15 B16, she got married, changed her name, 2014. This is like, I would say it's like the Twin Cities. If you or anywhere you say Twin Cities, right? Not Richfield, Bloomington. If you don't know it, it's like somebody say Twin Cities, say Richfield, Bloomington is a Twin Cities. That's how bad this is if you don't know this table. Okay, knowing how to use it is more important than knowing it even. I have a couple of rules, guys, that go over to use it. But before we use the rules, I want to remind you that these are the temperature rating of the conductor, 60, 75, and 90. Okay. Now all the conductors inside, underneath them are either, like for example, here's a conductor rated. Let's just use this one. Conductor rated for, this is a 60. This guy, if you put two H's in it, that guy right here, THHW, that becomes two H's are 75. If you put THHW, this one, THHN, that will get you 90. Actually, one H is give you 75 here, right here. One H, THW, this is 75. And I'll tell you why THHW is also there. And THHN is 90 in addition to all these. This is your copper side, and this is your aluminum side. So make sure you know the aluminum and the copper side. Um, so here's how they catch you. If the conductors, I want to bring to your attention this weird conductor here, right here. Can you guys see? Look at this conductor. How is it looking on your side? This is THHW. Is this a bad color? This is a bad color. And look at this conductor here, right? Same conductors are in two columns. When do you use it? This means, guys, if it's used in wet location, it's 75. If it's used in a dry location, it's 90. This is one of the most important things that we catch you on. One of them is THH. Another one is XHHW. Can you guys see that? What is that? There you go. XHHW, XHHW. Everybody can see that? These two, they are on the two columns. I want you to highlight this one here. Can you guys XHHW-2? This dude, when it has dash 2, and anything that has dash 2, yes? So, but they wouldn't tell you. They would tell you a feeder on a roof or an underground feeder. A 4-aught conductor is an underground feeder. How much current does this conductor can carry if it's 4-aught underground? 4-aught underground, right here. 4-aught underground. Where is the conductor? Here. If it's 4-aught, I didn't say underground, in a building, it can, well, for derating purposes, it can carry up to 260. It wouldn't carry it, but you can use that. Please clarified. Um, a table. So this is the first table that you guys must make sure you know how to use it. This is for ambient temperature 30 or 85 degree, and it says also for 3 current carrying conductors in a raceway, cable tray, direct buried, you name it. So there's limitation on the temperature, limitation on the number of conductors. We'll get back to it. This table will tell you guys the temperature rating of the conductor. For example, I'm going to go back to this. Here's THHN. It tells you it's rated for 90-degree damp or wet location. Here's my THHW, wet location 75, dry location 90. Can you guys see that? Everyone can see that? X, where's excess? Here's the W-2, the one that has dash 2, 90-degree, dry or wet. Bring it on. How about if it was just THW, 75? God forbid you have cable. Where's you have cable sitting? 60. I want you to highlight this one because it's very, very important. This one here, guys. Right here. Um, this is 310.104A. 310, got it? 310.104A. Sorry. Give you enough time, guys, to make sure you highlight that table. Okay. Everybody highlight the THHW and knows the difference between wet and damp location. XHHW-2. XHHW-2, guys. Do we have to worry about wet or damp? So how about XHHW? Here's your dry or damp location. Here's your wet location. Okay, so the first thing you need to know is wet or dry. Now let's go to the rules. Everybody's good? Let's go to the rules. 60-degree column. I'm going to be jumping. Go to 3. Make sure you guys are at 310.15b16 because that's what we're going to be talking. You can summarize this. When would you use this? Okay, here's what we're talking about. So everybody on the same page. We're going to use when do you use 60, when do you use 75, and when do you use 90. Everybody understand? Okay. All right. So let's go to 60-degree rules. 60-degree. You must use 60 under the following condition. Number 1, if the conductor insulation says 60. You guys hear me? If you have TW, UF, do you even have a chance? 60. You're doomed. If the terminal says 60, if they tell you the termination, the logs on the piece of equipment are rated for 60, you're doomed, regardless of what your installation is. If you have no idea what the installation is, and the conductor is number 1 at or 1 or less, yeah, they don't tell you what the installation is, but the conductor coming to the piece of equipment is 1 or less, then you must use 60. If the terminations are unknown and the equipment is rated for 100 amp or less, then you are coming from 110.14. These are not from my basement. These rules, I summarize them from section 110.14. And then, all right, one more time. If your installation is 60, don't think about it. If you know what the termination are, conductor say column. Okay, so you go back to 60-degree column here, and you start with number 1 right here. If you're number 1, you're stuck basically. If you're conductor from number 1, you are in the 60-degree column right here. Unless you know what the logs are and the conductors are rated for more than 60. All right, now let's go to 75, gentlemen. 75. Now, to use the 75, the single most important thing, then your conductor insulation must be 75 or 90. I can't emphasize. We decide you want to use THHN. That's 90. Now you go to rules. Rule number one. If it says the lugs on the machine are rated for 75, then you go 75. But remember, the installation first must be 75 to go through these rules. Okay, or if it's a motor, if you're designing a motor and it's designed B, C, or D, B, C, D motors are by code 110.14 tells you these guys UL list them for the lugs on them for 75, so don't worry about it. Or if the termination have no idea what the lugs are rated for, but the conductors coming out of the machine is more than one. There will be 1 aught, 2 aught, 3 aught, 4 aught. Once you see anything on the aughts and higher, then and the installation are 75 or higher, where do you go? You're going to go directly into the 75. How about if the termination are unknown and the piece of equipment says 110 amp piece of equipment? Where do you go? And your conductors are rated, conductors are THHL or THW, you go to 75. These are the rules for using the 75. So once you go to the 75, gentlemen, basically 75 start right here. From here on, this is when we start using 75. Does that make sense? From here on, you start using the 75. But don't forget the rules, though. The rules for the 75. Okay, 90. 90, when would I use 90? The only time you use 90 is if your installation are rated for 90. Otherwise, don't think about it. And what do we use it for? Do we use it to size under normal operating condition? No. You always use it to what? Derate. Okay. So you use it only to derate. How do we derate? When we derate, guys, when we derate, conductor ampicity is determined by the installation, must not exceed the normal operating condition. These are probably one of the most can't exceed the normal operating sizing condition. The last thing about them, guys, all conductor rules. No matter what your overcapacity device come up with, you can't cover by the way. Okay? The law number is rule is what? Orders. Yeah. Well, the code, both the motors and exception. Anybody know that slip overload? So the conductor will be protected by overload. Excellent. Okay. Any comments, guys, questions about the rules before we start? These are very important rules of engagement when it comes to the motor, to the ampicity. Yeah. Well, let's give you an example here. Let's see a very quick example here. Um, let me just change my color here. Oh yeah, the termination. Yes. So I'm going to tell you guys. Here's how much current a 250 amp conductor can carry. and I decided to use a THHN, oops, THHN, under normal operating condition for sizing. How much current that guy can carry? 255, right? I have no idea what the lugs are. So the conductor is more than number one. So that would be 255. How about if I want to use it to derate? Which amp should I use when I use it to derate? 290. Am I making sense, guys? When you derate, you start with 290. When you size, you start with 255. All right, let's take another example. Here's another one, number 6. Number 6, have no idea what the lugs are. The installation is THHN. THHN. So it's rated for 90, right? So when I size equipment normal operating condition, how much can I size this equipment for? 55 amps. Now here's a trick. 55 amps for normal operating. How about if I want to derate? Which amp should I use for derating? 75. Why? 55 shall not use it. That big deal. That's when you start. Five out of it. Okay. Here's an example for you. I have this number 2 conductor, THHN, THHN, feeding a design B motor for normal operating condition. Where do I go for that? Because it's feeding a motor. 75, 115. How about if I want to derate? There's bundling. Where do you start when you derate? 1/3. After you start with 130 though. 120 out of it on the normal, out of it on the normal. Okay, 100 amp. Let's just take 100 amp. Okay, I have 100 amp continuous load. So that would becomes what? 125 amp. Everybody knows why, right? You multiply 125 amp. Okay. Now I need to size a conductor for it. Let's just. I decided to use THHN. THHN. Okay. THHN and and let's just say so THHN. So I'm going to go to which side now? 100. It's more than 100, so I can go to 125 under 75 degree. 125, that will get me, here's 130. Can you guys see that? And that will give me number 1. 130, that will give me number 1. If it's THHN. So that's my conductor is 101. Um, so, uh, so I can get my 100 and number 1 will be my conductor. Number 1 will be my conductor. Any comments, guys? Any questions? If my THHN conductors are THN is my conductors, and because it's more than 100 amp, I went to 75, and that gives me number 1. So, okay, so let's go take a couple of examples here. Yes, we got that. All right, addicts and all this good stuff, guys. All right, now derating. Derating. There are 2 tables you guys must highlight before you start using Ampicity Business. This table is, oops, give me a different color. This table right here, and this table. All right. So ambient temperature. If your ambient, let's just say I have an ambient temperature of this. Okay. Suppose I have a 100 amp motor, now 100 amp piece of equipment, cable, and the ambient temperature for that cable is 122. Now, if this cable is THHN, right? How much current can I pull out of that dude? 0.85, 0.82. If my conductor is THW 75, I can pull 75 out of it. If all hell break loose on my conductor is TW, how much conductor current I can pull out of the same conductor? 0.58. Temperature insulation. It's all the time. Any comments, guys? Any questions about? No. Uh, can carry no more than. Now, the second table next to it, guys, is for putting things on a roof. If you putting conduits on the roof, your conduit will be cooked by three fires, basically. Number one is, or three currents, or three heating source. One is by the current going through it. The second thing by the sun beating on it, okay? And the third thing is by the reflected heat from the roof. So the smarter than Chad discovered that these conductors must be boiling down there. So now they want you to do it. That came in 2011. How do you do it? Okay, let's just say you decided to put a block that raised your conduit on a roof up to say 3.5. Say four. Let's just say 4 inch block. We put it there, and then you need to your ambient temperature 30 degrees. So if you're Minneapolis, ambient temperature 90. For derating purposes, now you add a 30 to it. It becomes what? Now it becomes 120. They call it temperature adder. It becomes 120. Now, if you decided to put it right on the roof, no, nothing, look what happened. You have to add 60 to your ambient temperature. So you're in Minneapolis, 90, add 60 to it. Now you're sitting at what? 150. Okay, look at the 150 where it put you here, guys. Now 150, you're right now here. So look what happened to your cables. Now you lost almost half of the amps in any cable that you use there. Any cable. Even the best cable that, say if you're going to use THHW-2, which is rated for wet location, that give you 90 degree in both wet and dry, you still lost almost half of the Ampicity. Do me a favor. This exception is not under the table. It's in the text itself. Make sure you highlight it. This table, there is an exception for this table. This exception, guys, XHHW-2. One more time. Is a robust wire that can handle all this stuff. Now, what if you're using THW? THW. I need somebody to correct me. We're on the road. What if you're using this type of correction? Can I use THW on the road? Now remember, THW, guys, is what? Rough is what? Wet. You can't. You will do it. You're right, but we can't use TSHN on the rough. TSHN is not a conductor that you have to have a W in the end. Step that one. The exception should be uh, look at it closely. This rated for the wet appeal. I just put underneath the table to make it clearer here. I guarantee they'll test you on that one, guys. You will guarantee it because that was changed in 2014. Well, ignored that. Yeah, you have to do it. Yeah, I see the confusion. If it's bundled, you derate. If it's on other temperature, you derate. You just don't add more temperature on and off only. Okay, gentlemen, we have a TW cable supplying a 40 amp um, uh, load in the attic, and the ambient temperature is 113. What size cable should we use? Okay, so I should emphasize. Okay, so there's load. Here's my load, and there is conductor. Conductor. There's load and there's conductor. If you're trying to find, look what happened, guys. If you have the load and you need to find the conductor, you must divide by the derating factor. If you have the conductor and you need to find the load, you must multiply by the derating factor. Divide, I'm going to say D here, multiply by D. One more time. Okay, so TW, where are you guys going to go? What's the derating factor for TW? Under 60-degree column. Why do you go to 60-degree column? TW, you have no choice. So your derating factor 0.71. Gentlemen, then you take 40, divide it by 0.71, you end up with 56.3. Now, once you get to 56.3, which column do you want to go under 310 or 15B16 and why? You need to go to column. Anybody knows what column? 60. Why 60? Why not 90? Well, the conductor is THHN. So it will be number 4. I'm sorry, TW. Now, let me spice it up for you guys and say, let's make this one THHN. What changes? THHN. Okay. Now, same thing. What would the factor be? The factor here will be different, right? And then when you go here, you go to the 90-degree column. You guys see that? The conductor can exceed. We didn't say anything about continuous here. It's under 60-degree column for two reasons. Number one, because for the THHN or for the TW. For the THHN, it's because it's less than 100 amp, and we have no idea what the lugs are. Yes, yes. If it's less than 100 amp, regardless of what your installation is, under normal operating condition, no derating, you're stuck with the 60-degree column. Oh, can you give me that number, please? Can anybody give me this number based on 90? The rating factor. How much? 0.87. So this number become 0.87. Okay, cross this one then. Then I need somebody to we cross this. And can you guys give me the answer for this, please? 0.87. What would this answer be? Divide 4. How much? 45.9. Okay. Now go to 310.16 under 90-degree column. Go to the 90-degree column. Give me the number that you got, the conductor that you got. How much? Number 8. Okay. Now do me a favor. Okay, don't stop there. Now you're gonna go take number 8. Under number 8, under no, what's the normal operating condition for number 8? 60. You mean 60-degree column, normal operating condition. How much current can this guy carry? Under 60. 40. Okay. What's you see that? 10, for example. Say I came up with a point. All right, what's the ambiguity of number 8 THW supplying a rooftop, and we have a distance from the roof of this, and the conductor is this type. Remember, pay attention to the type and this conductor. And here's the ambient temperature. So what do you need to do? You need to add. There is a temperature adder. Temperature adder. All right, gentlemen. So you need to add a temperature. For 6 inches, we're doing Celsius here. Don't ask me why. 17 degrees Celsius. And then you add the 17 degree to the 38 existing. That'll give you 755. You go to table 315B to 8. That will get you a derating factor of 0.67. Right? Everybody understand that? We just added temperature. And then, which column are you going to go to find the ambiguity of 8 THW and why? Which column and why? Number 8. I needed an ambiguity for number 8. Which column are you going to go to? 75. Why 75? Yeah, and because we're derating. Once we derate, you go strictly by what the conductor is rated for. Now, under normal operating condition, here's what confusion. Go to find the ampicity of that conductor. And then multiply it by the rating factor, I get 33 point. Now, once you get there, I would like you guys to go to number 8. You need to check number 8 under normal operating condition, which is 60. How much current can you carry? 40 amps. The normal operation of the conductor rules. That's here. And then you do the rate, whatever you come up with, you can't come up with what the conductor under normal operating condition can carry. Okay, what is the ampicity of 250 kcm XHHW in an underground PVC installation? What would an underground indicate to you? What? And then now XHHW is rated, has two temperatures. Even for derating, can you even now here's, I want to spice it up. I see it. Rating purposes. For rating purposes, it will be 90. For sizing purposes, it would be what? 255 normal size. Okay, we got that one. Everybody's good. Now, current carrying capacity. The NDC code book, guys, when you have a cable, all have heat on them. Heat is enemy number one of electricity, right? So they will fail. Conductor insulation would deteriorate over time, and it will fail and shorten ground fault. Okay, so here's the table that you use. If you have never seen that one, again, you're a plumber, but make sure you go highlight that one and know how to use it. All right, number of conductors. If your conductors are 4 to 6, you have to derate them by 80%. So it's really easy. What happens if you have a 50 conductor in the same conduit? Look what happened. You get 35 cents on every dollar that you put there. To give you an idea, who's in his right mind would do something like that? So if your conductor is 100 amp, you can only use 35 amps out of it. That's crazy, isn't it? So typically, guys, we rarely, if ever, we go higher than that. That's kind of where industry standard. 9 hots give you 70%. Using the 90-degree column, it makes sense. In the wireways, you can go up to 30 hots in the wireway without derating. So, but going higher than 9 conduct hots in one conduit, you're losing 50% of your cables. It's not worth it. Yeah, yeah. Yeah. You're just using. Can you? Yes, you can. So because if you're using number 12 and you cut it by half, look at that. If you're using number 12 and you cut it by half, you still have 15 amps out of it. So number 12, for example. So sometimes we even get into this area here, gray area, because especially with number 12, because number 12 cut it by half, give you 15 amps. If you have a 20 amp circuit, that's not bad to pull 15 amps out of it. But really getting into higher than 50 becomes not cost effective. Okay, now what counts? What counts, including spares? If you have a spare, if they tell you guys there is a spare in the conduit for future use, what do? Count it. So on the test, if they tell you there is a spare that's going to be used for a hot conductor or even neutral conductor, you can use it. Shall be adjusted. The count shall not include conductors that are connected to electrical element but cannot be simultaneously energized. Okay. This is also changed in 2011. Three-way and four-way switches. Simultaneous. Another example. Look at the language when they tell you about it. Okay, forget that one. Next, number 10, THW cover current conductors. What is the emphasis of these conductors? They're TH. Yeah, why not 60? Because we're derating. When we derate, guys, we go strictly by where the installation puts us. We don't worry about the normal operation, right? All right. So how many conductors? There's six of them. So you find for six of them, it's 80%. You then under 75 give you 35. Then now you can't carry more than 28. Now, here's my question for you. Once you do there, then you go ask yourself number 10 under normal operating condition has to be 60. How much current can number 10 carry on the 6-degree column? Is it 30 amps? 30 amps. Now I want you to look at these two numbers and compare them to each other. Have we exceeded the normal operating condition of Okay. What size TW cover conductor installed in a single raceway shall be selected to feed three-phase 50 amp freezer, assuming non-continuous? If it was continuous, what would you do? You size based on 1.25, put it aside. Then you go size based on the rating and find the answer. And what do? Pick the largest of the two. Okay, so in this case, it's not continuous. So for nine of them, there's three conductors, three phase each, three feeders. That will be 9. The derating factor is 0.7. TW, you have to go to 60 because you're doomed. And then you need to find the conductor. So you divide or you multiply. When you have the load, you need a conductor. You divide by the derating factor. So which you up the current, so you can have a bigger conductor to accommodate. So it'll get you 71.4, and that'll get you number 3. That'll get you number 3. Now let me show you something. I'm gonna go change this one, guys, quick to THHM. I need your help with it. THHM. All right, everything stays the same. Now the only thing comes is, can you guys, so 75 right here. So now from here, which column are you going to go to? Since THHN, 90-degree column. Go to 90-degree column. What's the conductor size, please? Under 90, 71.4. Number 6. Okay. Number 6. Now, before you get look at we started with number 3. That's a big jump, right? Now then you're going to go number 6 under normal operating condition, which is what? 60. How much current that this dude can carry? How much? 55. Okay. Have we exceeded conductor right here? Have we covered this number? Talk about how nice they can carry them better for derating purposes. Okay. Containing a conduit containing three phase 4-wire. Number 12, serving receptacle load. What is the ampicity of each conductor if the conductor serves nonlinear load? Okay, we have three phase. Let's count. 1, 2, 3, 4. Here's one circuit. And imagine 3 of these. How many conductors do we have? 12. Does the neutral carry? Count. Yes. If they say the neutral guys is carrying, the neutral is carrying a nonlinear load, which is harmonic rich load, then you count it as a hot. So these are 3 boots, and then they will count as what? 12. So here you go. So 12 of them. For 12 conductors, gentlemen. Number 12 carrying conductor. The rating is 50. THHN under 90 degree can get you what? 30. So we're limited to 50. So each one of these conductors cannot carry more than 15 amps. Not only that, it's supposed to go. Number 12, how can you guarantee that you have to go there and put the 15 amp breaker on it? 15 amp breaker instead of a 20 amp breaker. Yes. You don't tell them you do not. But here's how they catch you. They say a lighting load in a commercial building that feeds electronic ballasts. That's not it. Look for electronic ballasts, electronic equipment. That's where nonlinear load comes from. You see electronic ballasts, electronic equipment, anything that has to do with electronic VFDs, soft starts, any of these, they are offenders when it comes to harmonic counter neutral. Okay, double derating. Double derating is when you have a temperature and a bundling at the same time. No biggie. Okay, so race we has 6 number 1 aught, and an ambient temperature of this, and an insulation that sucks, THW. How much current can this conductor carry under these circumstances? This is the double hit. You have to cut first because of temperature, then cut second because of what? Bundling. All right. So because of 6 conductors, I have to cut it by 80%. So I lost 20% of my ampicity because of that. Now, because of temperature, I lost another 18% because of temperature. Lost 18% because of temperature. And the ampicity of the conductor, because it's THW under 75 degree conductor, that would be 150. So then my conductor, under these circumstances, cannot carry more than 98 amps. You you can't double the rate between continuous load and voltage drop and these. But these are the bundling and temperature are one thing. Like this is derating because of bundling and temperature. Yes, we're talking about heat here, but continuous load is a different thing. Yeah. All right. Here's an example. We have two sets, parallel sets. So we have two machines. It looks like, and we brought fed these machines from one feeder. Um, two parallel sets, 400 amp. Oops, actually the wrong way. No, easier to discharge and come back. So what happened, guys, is we have a machine that we're bringing two parallel circuits, sets of circuits for it. It's a 400 amp. Ambient temperature sucks. We put all these conductors in one conduit when we came to it, which is okay. So the question is, what conductor do I need to carry this machine? There are two parallel, two sets. So how much each set will be carrying by itself? 200 amp, right? We'll be carrying 200 amp. But then the problem is if there's no temperature correction, guys, what would you do? You take the 400, divide it by 2, because we're paralleling two sets, and then go to 310 B16 under which column? 75-degree column. Why? Because the installation is 75. And what else? What else? I need another thing. Yes, the equipment is over 100 amp, and you're done. That's if you were not derating. Am I making sense? Because we're derating, then we have to divide by the derating. Okay, the first thing you need to do is find the bundling, my derating because of bundling, and my derating because of temperature. I have to accommodate for these two. Then, gentlemen, then you divide. Can you guys see? Here's my load. You divide by both of them. Now look how my load got way blown up. Now instead of going and sizing a conductor or two conductors, guys, for a conductor for 400 amp, I need half of a 400 amp. I need to size for 66 amps. So divide this by 2. Why did we divide by 2? Because we're paralleling two sets. What happened if we're paralleling 3 sets? What would you do? Divide by 3. And I'll get you number 4. Now do me a favor. How about let's just make what would the size be if if there was no derating? Now remember, you need to cut them into 2, so that'll be 200 amp. Everybody knows why? Because we're paralleling 2 sets. So we have 2 sets, 200 amp. Is there a 4-aught? Right? I think it's 4-aught under is it 4 or 3? 3-aught? Okay. 3-aught. You guys see the gravity? We went from 3-aught into how much? 400 kcl because of bundling. Yeah, yeah. It'll be cheaper to do that. The what? Um, four. How many? Three. We have like 6 of them and 4 kcm. You might be able to put it in 400 now for EMT range. 6 of them are tight. It's the dumbest thing they can do. It's not just tight. Yeah, yeah. If less ground, it'll be very tight. Yeah. When the size is that large, guys, Separate conduit. That's the easiest way to do it. Okay. Any questions guys about this? Questions? We need a quick break or Rich, everybody? We take a very quick one? Let's do a quick one. Okay. Um, we talked about that one. What's the ampicity of three? Number one, odd copper conductor and rigid metal conduit supplying motor in an area with an ambient temperature of 135. Choose the one correct. So, supplying a motor. So we have ambient temperature, and we have three conductors. So one odd. So we have. Here's what we're going to do. So an ambient temperature, gentlemen. Let's see here. There is one odd, three conductors, one odd. Based on this ambient temperature, gentlemen, you got this. One odd can give you 150, so your conductors are limited to 85%. So 87 amps. 87 amps. Any comments, guys, questions about that? Well, um, if motors are continuous load, so under normal operating condition, how much current can this conductor give you? 150, right? Because it's motor and because it's the conductor one off is larger than number one. Now, if it's feeding a motor, remember, if it's feeding a motor, it's limited to 80%. That's the reciprocal of 1.25. So point times 0.8. How much current continuously you can pull out of this? The 120? What's 0.8 times my calculator? 0.8 times 150, 120. 120. Now I can't pull more than 120 out of it. So yes, you have to look at the continuous load and look. If you find the amps cut it by 80%. That's all. You read, and compare them. But in this case, that wouldn't change the answer, our answer. Speaking of the devil's continuous load. All right, continuous load. For continuous load, guys, we size the breaker as well as the conductor based on 1.25. All right, I have a 35 amp continuous load shall be supplied by what? Continuous load is not derating. It's a normal operating condition for the conductor. Okay, so when you size for continuous load, don't only look at the temperature of the conductor. You have to look at the lugs and everything else. All right, 35 amp TW. Which column should you go from the get-go? 60. You have no choice. So it's continuous, so multiply by 1.25, gentlemen. So you got yourself 1.25, got yourself number 6. All right, now I'm going to go change this one to THHN. What changes if my conductor was THHN? Look at it again. What would change if the conductor was THHN? Nothing. Nothing. Why? Because normal operating condition, you go first by the okay, the conductors allow me to go to 90. Then the question, am I derating? No, I can't go to 90. Then ask yourself then, do I know the logs? No. then I can't go to 70. So is the equipment rated for more than 100 amp? No. Then I have to go to 60 anyway. So it really doesn't matter what the installation is. Now let me spice it up for you. Now let's just say the conductor is feeding a motor. Okay? Look how this will change. Now we know it's feeding a design B, C, or D motors. By code, these guys, the lugs on them are rated for what? 75. My installation are THHN, which is higher than 75, which is good. Then can anybody give me the size, please? You're going to go which column then? You need to go to 75-degree column, and that would give me number, what? Number 8. Does that make sense? Or if I told you the logs are rated for 75, then you go directly to 75. But you have to be told that. Any comments, guys? Any questions about that? Comments? Okay. Existing number 8 conductor needs to be reused. What is the maximum? I have a cable right here, and I need to tie, it's already existing. I need to tie a machine to it. Okay, fuse disconnect, and I want to land it on a machine. It's an existing. This machine, I need to size, what size machine can I put it on? Okay, it's continuous load. So what do? You find the amps, and what do you do with the amps? You rate it by 80%. Or here's what you do. So it can get you 40 amps. TW can get you 40 amps, and it can get you 32. Now, look at that. This is a THHN now. THHN. Logs of this machine are rated for 75. I'm telling you, logs are rated for 75 here. And the breaker on this side is rated for 75. Okay, how much current can I put? And number 8 can give me. Now where do you go? You're going to go to 75. Can you guys find 75? Under 75, how much number 8 can give you? 55 or 50? Okay, do me a favor. Divide this by 1.25. 40. Now you can get 40 amps. By the way, dividing by 1.25 is like multiplying by 0.8. So when you say multiply by 0.8 or divide by 1.25, it's the same. Do you guys see how it's different based on the installation and the logs, not just the installation? I have to tell you anything about the logs. If I say it also to motor and the logs on both ends are rated for 75, then you go 75. What size THW is required for a 50 amp circuit, non-continuous, non-motor? 50 amp, non-continuous, non-motors. What do you go by? It's a THHN, so I can go, if I was derating, I can go all the way to 90 degree. I'm not derating. So you go by strictly by the amps of the equipment. The equipment is rated for what? 50 amp. It's 100 or less. Where do you go? Perfect. You go to 60. Now here's how I can. Now what if I told you this cable is tied to a piece of equipment that's motor design B, C, or D, or the logs are rated for 75? What would the answer be? Number 8? Number 8. Does that make sense? Okay, now we have a continuous load, and we have a derating because of current carry conductors. If you have two things at the same time, what did we say we do? We treat them separately, find the continuous load, size them separately, and choose the largest of the two. Am I making sense? So let's go size the load. It's a 25 amp. We need to find a conductor and a breaker. Look at this. We need minimum circuit conductor for that, and an overcurrent protection device. Maximum breaker. Okay, the breakers are size, guys, 1.25. Like for most motors, not motors, for most of equipment, 1.25 for continuous equipment. Okay. So the first thing you need to size for continuous load. Okay, here's 1.25. Here's my based on 135. Then you go to the next standard up. To size the fuse, guys, for continuous load, you multiply by 1.25, and then you go to the next standard up. Cool? All right, so now how do you size the fuse based on the rating? There's no calculation. Bundling and derating and temperature. It doesn't, the fuse doesn't, you can't size the fuse based on bundling and derating. You can only size it based on continuous load and non-continuous load. If it's non-continuous load, match it to the equipment amp. So your equipment is 90 amp, your breaker is 90 amp. If it's continuous load, your equipment is 90 amp, multiply by 1.25 and go to the next standard up. So, no, not common. But we go on the test, you go by 240.6. Yeah, go by 240.6. Okay, so we found the breaker. Now let's go size the conductor. Now to size the conductor, guys, we multiply for continuous load 1.25, so they'll give me this amount. Then you take this. Why did we go to the 60-degree column even though the installation is THHN? Anybody can tell me? Because the equipment is less than 100. Doesn't matter what the conductors are, normal operating. So give me number 8. So my first solution then, guys, would be based on bundling. Based on bundling, my conductor would be, oops, okay. Based on bundling, my conductor, is my conductor, this would be 35, and the conductor will be number 8. I'm sorry, based on continuous load. Okay, now stop there, put it aside, and let's go size the conductor based on what? Based on temperature. Okay, or bundling. All right, so I have four current conductors, give you 80%. So I have 225 divided by 0.8, that give me a bit, this number. So that will give you this number. Since we have THHN, guys, and we're derating, we can go all the way up to where? To the 90 degree, and now we have number 10. We have number 10. Okay, so I did two calculations. One came up with number 8, one came with number 10. Which one would you use? The largest of the two, number 8. And even you can't use number 10 on a 35 amp breaker. Remember, there's a small conductor rule that says number 10 is limited also to 30 amps. But it doesn't really matter. What matters is you did two calculations. One derating and one amp wise, the largest. So so based on in temperature, and then you can go to 6 degree, and also number normal operating condition for this would be number 8, and number 8 can allow up to 40 amps. So in a case like this, guys, your connector will be number 8. Why? Because it's the largest, so bundling and continuous. How about your breaker? The only thing that size your breaker is the continuous load or non-continuous load. The derating has nothing to do with your breaker. Nothing to do with your breaker. Okay, bedroom in a dwelling unit has an outlet for air conditioning. It's a 15 amp 120, and it also serves other loads. What's the maximum allowable AC unit you can plug in? When you have a window air conditioning, rich man's way, then two area. If you no longer individual circuit, load that circuit with so there you go. So I have my circuit is not 20, it's a 15 amp. I have to cut it by half because it says if it's equipment is shared, you cut it by half. That gets you this amount multiplied by the voltage, and that will get you 900 volt amp. So my AC unit must not be more than 900 volt amp, or I have to put it on a dedicated circuit. I think this is the one that can get you dedicated circuit, or one of them. Now, if my circuit is individual 20 amp circuit, then what you do is you take the 20, multiply it by zero point 0.8 to find the volt amp, and multiply it by 120. I think that will be 1440. Is it? No? 1920. Okay, so that's the 1440 maybe is if it's 15. So they put it to you as an option, guys. So you know, if you did the zero point 0.8, you'll find an answer you think you got it right, and when it's wrong. One more time. Shared circuit with AC units, 50%. Individual circuit to the AC unit is 80%. What's the minimum size TH and copper that supplies a 119 gallon residential 4.5 kW 240 system heater? If you look at the 119 gallon residential, this will tell you guys water heaters are considered what? Continuous load. So then that's it. So find the amps, multiply by 1.25, and size the conductors. Do we size conductor based on kW, kVA, or based on amps? Amps. But if we have the kW, what do we need to do? Find amps. Okay, there you go. So I have 45 kW. It's a water heater, so the power factor is 1. And here's my amps. If that was non-continuous load, guys, you're done, and you go size your conductor. But since it's continuous load, what do? Up it 25%, that'll get you 23. And then you go to your conductor will be 23.4, and your breaker will be 25. Your breaker will be 25. So 23. Now, when you find the conductor, the amps for the conductor 23, why did we guys go to this column? Yes, less than 100. That'll give me number 10. So number 10 and 20 amp. Have I exceeded the small conductor rule? Have I exceeded the small conductor rule? No, because number 10, you can go as high as 30 amps in it, as high as 30 amps. Any comments, gentlemen, questions? Quiet group. Okay, find the THW cover size needed for a 400 amp under 600 volt cable busway system. How many of you guys have installed cable busway system? Like a cable tray pre-manufactured. Appropriately as a system. That's considered working up in the air. It's based appropriately in a box. When you use the, which table would you use when you go to them? You have to use table 317. I'm not sure how many of you guys have used that table. That cable's in the air. All right, so For a 400 amp, I only need 250. Okay, here you go. So my equipment is 400 amp. I need is 75. 400 amp. Here's 400 amp. Can you see that? How much current I need to carry? 250. Now, if you don't know that, where would you be going? You're going to be going to 310 or 15B16. So make sure cable trays, cable busway system considered up in the air. They are like conductors in the air, and you don't use 310 or 15B16. You use 310 or 15B17 on them. Look how much 500. Look at this. If you have a 500 amp conductor, look how much current that dude can carry. Anybody remember how much 500 kcm conductor can carry in a conduit? I can tell you, it can carry 380 amps because we use it all the time. So we went from 380 to 620, almost doubled the amps if you put that cable up in the air, or in this case, a cable busway system, manufactured enclosure, spaced appropriately, heat can dissipate. The reason why we derate, they allow the conductors to carry less amps because you're trapping heat inside the conduit. There's no space. It's not like air where uh, cables can heat can skip. Um, okay, now the same thing, guys. It's a cable busway system, except not sure if anybody works with medium voltage cables. MV stands for medium voltage cables. 5K stands for the rating of that cable. There's 5K, 15, 20, 25, I think, and 35. So, do you guys expect TB16? It's limited to 1,000 volts. So there's another table, gentlemen. We're going to go to it right now. I will remind you, every table that we go to, guys, here's a table that we're going to be going to. I will remind you of its 15K MV cable and 90-degree. Okay, here's the table. It says Ampicity of insulated single copper conductor in the air. Voltage limit 5K. Temperature 90. And what was the current that we're carrying? How much? 400. And then you're going to go all the way to 400, and that'll get you what? 4 out. They'll get you 4 out. So if somebody tells you how much current a conductor like 500 kcm can carry, what would you think? If you put it in conduit 380, if you put it in a busway with a 356, if it's medium voltage cable, it carries close to 95. If the voltage any comments, guys, questions about that? Does that make sense? No, yes? Okay. Number 8, THW supplying a central air conditioning consisting of sealed blah blah blah. The branch circuit may be loaded to a maximum value. Individual circuit or HVAC equipment can carry that 80%. So conductor- the conductor is number 8. Why did they go to, well, here, look how this changed. What if I told you guys this is a THHF? Which column would you go to and why? Which column and why? 75. Why not 90? We're not derating. We're not derating. Otherwise, you would have gone to 90. Okay. So, what would number 8 can give you guys at under 75? 50? Everybody 50? 50, yeah. And then, of course, if you use 50 divided, multiplied by 48, that'll get you 40. Am I making sense, guys? I'm sorry. I should have also told you about the logs. Yeah, it's not enough to just the installation. The logs are rated for 75, or it's feeding a motor. The logs are rated for 75. I have to show you the logs or tell you about the logs. Okay. Using type NM cable, the minimum wire size behind radiant heating panels. Radiant heating panels, guys, in Article 424, 424, and it's considered working at 40 degrees Celsius. If you put your cables behind the radiant heat, it's hot. So they consider it 40 degrees Celsius. What do you need to do then? Derate. All right, my amps are 28, gentlemen. My amps are 28, so I need to go find the ambient temperature and derate it. Ambient temperature and derate it. Okay, so electrical first it's continuous, then appliance circuit 125, then I have to derate. So sizing based on its continuous load give you 35 amp, which is number 8. So 35, the size of a breaker is 35. So based on continuous load, you're done. You get 35 here, and your conductor get number 8. Now that's if it's size of continuous load, very easy. Raw mix. Raw mix, guys, if you go to the .80 raw mix, it tells you it's the worst of the worst. So regardless of the size and the log, you must go always to where? 6 degree column. Now we size this, we put it aside. Now we need to go size the conductor based on bundling. Okay, based on bundling, gentlemen, um, these heating panels are considered to be operating at 40 degrees Celsius. Based on 90-degree column, they'll get you 0.91. If you take the 28 divided by 0.91, give you 30, almost 37. 37 under continuous table 3 to 15 P16, you go to 90, they give you number 10. What's wrong with number 10? The number 10 anyway. So your conductor will be based on termination, temperature rating. Your conductor had to be number 8. Your conductor had to be number 8. Number 8. About the Ampicity. Comment. The last one related to the Ampicity, that was on my master when I took it. Is how much amp can a cover bus carry? A cover bus. You probably guys have seen cover buses. The length can be anything you want it to be, and the width and the depth. There you go. So they're giving me a 6 by 3/8. The key point for this one, guys, if it was copper, it can carry a square inch of it can carry 1,000 amp. If it's aluminum, a square inch of it can carry an 800 amp. Cover aluminum. Um, what did they give for 700? I'm sorry, 700. I lied to you. 700 if it's aluminum. 1,000 if it's copper. 700 if it's aluminum. All right, piece of cake. Then here's the dimension of that cross section area multiplied by 1,000, give you 225, 225. If it's aluminum, what do you do to it? Multiplied by 700 or 70%. Aluminum is 70% of the copper. Aluminum is 70% of the copper. Could be right here. 366.23a, I believe. Should be in there. Okay. I want to switch to cable to voltage drop, guys. Can we take 5 minutes? I'm going to swing to the restroom, guys, if you don't mind. Eat my sugar. What Ampicity goes like this. So make sure about the rating. Number of conductors, the rate. So they will tell you um, 14 conductors. Number 12. Um, number 12. And they're coming out of a multi-wire branch circuit. Branch circuit. Multi-wire branch circuits. Non-harmonic. Multi-wire branch circuits. How many current carrying conductors in this conduit? So you have a conduit carrying 14 conductors, number 12. You're using multi-wire branch circuits. And how many current carrying conductors you have? Okay, remember a three-phase. So here's 1, 2, 3, 4. Here's one first circuit. 1, 2, 3, 4. Here's the second circuit. We're up to what now? 8. 1, 2, 3, 4. Here's the second circuit. We're up to what now? 12, right? And then actually it's 15. And here's 1, 2, 3. We're up to, are we 15 now? So how many current carrying conductors? Now no harmonics. We have 3 here. We have 3 here. We have 3 here. How many do we have here? That's exactly what they want you to think. That's exactly what they want you to think. See? This is 3-phase circuit. When you have 2 hots sharing a neutral, you count a neutral, right? That's 3. See how they trick you? So this is will be carrying 12. If these are harmonic loads, it will be 15, all of them. So I can't remember if it's 15, but there's a number like this, like that. End up with 2 plus a neutral, because you have a neutral here that doesn't count, a neutral here that doesn't count, a neutral here that doesn't count, and then when you come with a neutral here, oops, it counts. Is that devil that come up with something like this? So be very aware of that one. They'll tell you that. So okay, voltage drop. Voltage drop, guys, is requirement of, believe it or not, building code, because it's part of the energy code in Minnesota. Voltage drop requirement is required by energy code in the commercial building. You take 3%. In the NEC code book is suggestions, believe it or not. But in the building code, it's a requirement when we design system. On feeders, 13. Total feeders plus branch circuits is 15. 5. So you can either have 2, 5, 2, 3, or 3 feeders branch circuits. You can have 2, 3, or 3, 2. Right? You can't have more than 3 on any one of them. You can't have 3, 3. Right? Or 4, 4, 1. You can't have more than 3. For all the calculation that we do, guys, on the test, you're allowed to use 3%. So you know. Voltage drop kill over CM. Remember that kill over CM? What happened if this was a 3-phase? What do you do with the 2, and what happened instead of the, what do you put there? 1.732 because of 3-phase. You guys all, L is length in feet, not meters. I is current in amps. CM is cross-section area. Well, it's not really. It represents the size of the conductor in circular mill. K is a factor of the impedance, the resistance of the conductor, the wire. You shall not remember these, but typically they are 21.4 for aluminum and 12.9 for copper. Don't remember them. If they want you to use K, then they will give you the K. If they did not give you the K, this means you don't want you to use the K, so you have to use the rel. Remember, there are 2 formulas, either kill or rel. Kill over CM or rel over 1,000. If you don't have the K, what do? Use the rel. Okay, here's the rel. Speaking, always wanted to switch that one, so R just to rhyme with the other. Here's your rel. R for resistor, I for current, L for length, 1,000 because the R is given in thousands, and 2 if it's single phase. If it's 3 phase, what do you do with the 2? Open the window, throw it out, and what do you put there? Okay, where do you find R? Table 8, chapter 9. That's where R are. Table 8, chapter 9. That's it. Where do you find K? Given. K is given. All right. It's a single phase, 120. 2 conductors, number 6. Length is 125, and K is given. I can't think of an easier problem than that. This is 2 kill over CM. Now there's one little problem. Where can I find the CM for number 6? Table 8, chapter 9. So the first thing you need to do, gentlemen, is go to table 8, chapter 9, and from table 8, chapter 9, you can find the circular mill, which is 26,242 circular mill. Whoever came up with the circular mill must have been drunk. Have you ever seen how they calculate the circular mill? It's just, when they do the millimeter squared, guys, you take the area of the conductor like a circle. Pi r squared, done. Find the circular mill, 1/8 of, it's 1/1000th of an inch squared. That's how a circular mill. So anyway, it doesn't matter. So you plug them in. This is once you get the circular mel, guys. Then you shall remember kilo over cm and 2 kilo over cm. Plug them in. Now your voltage drop end up 1.1 volts. Is this good, bad, or ugly? How do you know? No problem. You shall divide it by the source voltage, the mother source voltage. So if we got 1%, is this good? Yes. What's good? What constitutes good? Anything 3 or less is good. More than 3, bad. So that's it. That's how you calculate it. Straightforward. 2 kilo over cm. Three phase. Here's your formula for three phase, gentlemen. The only difference is, anybody can see the difference is what? 1.732. Why 1.732? Because, by the way, three phase will calculate the voltage drop between phase to phase. Single phase calculate the voltage drop between phase and neutral, or phase. Like, what happens if you have a 208 circuit? You have a heater sitting there at 208. 208 single phase. Which formula would you use? Single phase, even if it's 208, right? So if it's 240, which one? Which voltage? 240 single phase. Use the single phase. Because 240, guys, single phase can come either hot and in neutral or two hots, right? Single phase can be phase A and phase B, that's single phase. Or phase A and then neutral, that's also single phase. The only time you get three phases if you cut the three phases, A, B, and C. So just be aware of that. All right, gentlemen. The other one is rel. Here's your rel over 1,000. Where do you find R for the rel? Chapter 8, Chapter 9, Table 8. Chapter 9, Table 8. Okay. Phase. Um, when you do the voltage drop, which voltage would you use? The 120 or the 2A? Always the highest voltage for three phase. Phase to phase. 2A. It has, the conductor is 250 aluminum. The load, okay, there are two amps. Here's confusion. There's a load amp and a panel size. Which you use? Would you use the panel size or the load amp? Always by load. Okay, so don't get confused by the two amps here. Which amp are you going to use? The load. You're after the load. And here's given. Is this, and the length is given right here. Is this a kill or rel? It's a kill. Why? How do you know? The K is given. If K was not given, what would you do? Well, so here you go. 250 kcm. I had one of my students have done what he asked me, Chad. There is no, where can I find the circular mil for 250 circular mil kcm? It just made a mistake because it's not on the table. Oh, 250 kcm is 250 circular mil. Okay. You plug them in. So here's your voltage. Is this voltage good, bad, or ugly? How do you know? You have to divide it by which voltage, the 208 or the 120? The 208. And you get 3 point. Is this bad? Yes. Why? Higher than 3. What would you do to mitigate the situation? You go to the next standard. You go to 300 kcm and recalculate again. And see what you come up. Most likely you're very close. If you go to 300, you will make it. Okay. From the same formula, gentlemen, they can ask about the wire size, the distance, or the current, or the voltage drop. Any one of these. You have to learn how to flip the formula, which you guys are formula flippers experts now. I'm going to do one last example for flipping a formula according to my flip. So suppose I need to calculate the current. You isolate the current here and you drop it right here, so they'll give you I. Don't forget to go right, left to right, and they'll give me voltage drop. Anything at the top with I, all this junk, comes and rests in peace under the voltage drop right here. So that would be what? 2R. Did I miss anything? I, right? No, L, right? I'm sorry. Well, I'm calculating. Let's just say the length. I highlighted L. Doesn't matter. So that would be I. So if I want a length, so drop the length. What else? The last thing, guys, is rest in peace the 1000. So what do you do with it? Flip it, and where does it go? Up or down? Up. What's at the bottom goes at the top. What's at the top goes at the bottom. So this will be what? 1, 2, 3. Where's the 1? Missing a 1. The 1 doesn't show up. Okay. That's it. Does it matter that it's on the right side, guys? Flip it, it becomes on the left side. Have you ever tried to read from right to left and say like solving problems, drop voltage? That'll be interesting. So, okay. So R, let's go highlight R. Um, this is the table that you guys, this is chapter 8, table 9. This is where the size of the wire is. This is the area in circular mill. Make sure you guys highlight it. Let's take an example. Number 12, can you guys see number 12? If it says the quantity, number 1, this means it's solid. The quantity, number 12, this means it's stranded. Everybody can see the difference between solid and stranded? All right, let's go to DC. Here's the resistor for Mr. Copper or Mrs. Aluminum. Your default is always coated or uncoated. It's coated and uncoated. Unless they tell you it's coated, your default is what? Uncoated copper. What's the impedance is for a solid copper, number 12 is 1.993. If it's stranded is 1.98. Okay? Make sense? Now if it's aluminum, you have 3.18 and 3.25 for solid and stranded. Am I making sense, everybody? Can you guys see how to find R? This is table 8, chapter 9. Table 8, chapter 9. This is where one of my students asked, because do you see there's no circular mill here on this area? He said, where do you find the circular mill for 250 and after? He got confused. So, because they are in circular mill. Any comments, guys? Any questions about this? As long if you're given a key, you must use kill. If they give you the key in the question. If you're not given a key, you must use R. Real. Very clear. If you have a key, you use it. If you don't have a key, you have to come to this table. As long as we're on this table, guys, I want to bring to your attention a couple of other things. The diameter here and the area. We use this one later when we size conduits. We use it. We use the diameters when we size cable trays, and the cross-sectional area when we size conductors. That's it. That's how you find the. Now we're focusing on the resistor. That's how you find the resistor. Okay. I also. How about the circular mill? You need the circular mill for number 12. Can you see the circular mill 65, 30, 65, 30? Same. The impedance is different though. All right, everybody got that table? What you need from the table? Okay, I have 120, number 12 conductor, 16 amps is the load. What is the recommended? How far can I pull the 16 amps? If I have 16 amp loads, I want to wire with number 12. How far can I put that load away from the panel? So this is this a kill or a rail first? It's a kill. You need to flip it to find the distance. Okay, we just flipped it. Number 12, guys, from chapter 8, table 9. Chapter 9, table 8, give you 6530 circular mil. Voltage drop is 3. In order to put the voltage drop in the formula, guys, you must convert the voltage drop from a percentage into actual volts. So 3% of 120 is how much? 3.6. Okay? And then what's your load? Your continuous load out of the breaker that you can get is 16 amps. So these are the two things that you need to find. You need to find your load, and you need to find the acceptable voltage drop. How do you find the acceptable voltage drop? It's always 3%. 3% of the source voltage. So if your source voltage is 480, just take 3% of it. All right, gentlemen. Now once you do that, you have to flip the formula. Remember how we just flipped it a second ago. Then your formula looks like this. Then start plugging. Here's your circular mill. Here's your voltage drop. Where did you get this number from? This is right from here. The 3% of 120. Here's your 2 from the formula. This is from given. Where did you get the amps from? That's from here. And gentlemen, you got this number. You have two options now. Either you go to your options. Your options is you go to 57 or 56. I want you guys to tell me which one you should go for and why. The multiple choice. 57 or 56? 56. Why not 57? You exceed. Thank you. You go to the next standard down. On the test, they wouldn't give you exactly something like this, guys. 56 or 57. You have to go to 56. Okay. I have a 208. It's a 3-phase. It's the amp is 35. The distance is this. What's the recommended copper conductor? And you're giving K. We need to find circular mill. Remember, guys, the voltage drop and circular mill. If you want to find them, you just swap them. Swap them. Okay. Here's the 3% acceptable. Take 3% of 208. They'll get you how much you can lose. Then you need to drop. Then you flip the formula. Now here's a circular mill, gentlemen. Formula in the form of a circular mill. All right, so here's the 3-phase component. 12.5, that's Kel. Here's the amps. Here's the L, the distance. 2 point, where did this number come from? That's the voltage drop in volts. When you plug in the voltage drop, guys, in the formula, it's always in volts. If it's in percentage, you have to convert it to volts. Okay, gentlemen, then you do your math and you get yourself a healthy, this number. Now you go to Vikings or Gray Bar asking for a conductor like this. You think you came from the moon. So you need to convert this one into actual size. Where do you go? Chapter 9, table 8. Do you go up or down when you're there? There is no 1870, exactly 18798. Would you go to next standard up or next standard down? Up. Why up? Safer. What happens if you go down? That's smaller conductor. Can't go down. So that would be number 6. Everybody can see, guys, from the table that we're looking at. That'll get you number 6. Okay. One more example. We have a 3-phase 480. The panel is 100 amp. It's 1/0 aluminum. The distance is 550, and K is given this way, and we need to find the amps, the allowable amp. They're giving you an amp of a panel. Remember, you're not looking at panels amp. You're looking at what? Loads amp. So you need to flip the formula to get you the amp, right? We've done that. Okay, first you need to convert the 3% into actual voltage. That's how you do them. 3% to 480 give you 14.4. 1/0 translate to this amount of circular mil. Flip the formula, which you guys have done. You and I have done that one. Flipping the formula in the form of an I to get you an I, and then plug them in, and you got yourself a 75 amp. Okay, here's my question. Your option is 76 or 74. Which one would you choose? That's how much current you can pull without exceeding. Would you go 76 or 74? 74. What happens if you go 76? You will exceed the voltage drop requirement. Any comments, guys, questions about the voltage drop? Voltage drop is really cool. Easy to use. So one more. Am I going too fast? I'm sorry. A bit. All right. The only difference in this example, guys, we need to find the voltage drop. It's a 483 phase. Here's a conductor given. It's a kill. The distance is given. The only thing that's not given is, or given in different format, is the load. The load is given in kW. So what would you do? Piece of cake, find the load in amps. You can't put the 25 in the formula. You need amps. So first find the load in amps. Okay, well, here's the number 8. Here's you need the circular mil for it, which is easy. Then take the kVA. Here's the kW. Divided by the voltage and 1.732. That'll get you 30 amps. You have to find the amps first. Okay. Once we get the amps, you plug them in. Here's your amps coming in here. Here's the circular mil coming in right in here. The rest of them is kill over CM. 1.732 kill over CM. And I'll get you 7.3. Is it good, bad, or ugly? You don't know. So how do you know? Go drop it over the voltage, and that will get you what? 1.5, 1.5%. Any comments, guys? Any questions about that? Why? I'm coming. Is that 60? I'm coming to it. Yeah, yeah, yeah. Oh, yeah. I'm going through them. No, no, no. I have 2 more, and then I'll jump to the next section. Speaking of the devil, 61. We're coming after that will be 62. Okay, I have here's the voltage. It's a single phase. Here's the distance. Here's the amps. They're giving me the impedance, guys. When they get you the impedance, the R, is this a kill or a rail? It's a kill. So I'm sorry, a rail. Here's your rail, and here's your impedance. Remember, the impedance is given in thousands, so that's why we divide by 1,000 here. So the impedance is given in thousands. So look at the bottom here. So 2 rel over 1,000, plug in the 2, 1.24 times 11 times 200 give you 5.46. Is this good, bad, or ugly? You have to divide it by the mother voltage, and I will tell you if it's good, bad, or ugly. Any question, guys, about the voltage drop? Voltage drop. All the way to 2. All right, I have 120, single phase, 11 amps, 200 feet from the source is supplied by number 10 XHW. What is the voltage drop? And it's stranded. Stranded. You guys see the word stranded? Stranded. Okay, do you have a K? No, so this is clearly real. Okay, so here's my rel. Okay, here's my 2 rel over 1,000 from table 8, chapter 9. Now don't forget to go to stranded, will ya? So you have to go to stranded, not solid. How do you know if it's stranded? There's 7 next to it or 1. That will get you 1.24. Okay? That's the impedance. Once you get the impedance, gentlemen, once you get the impedance, then here's your impedance. You plug it into the rail, and your voltage drop is you're looking at it. Any comments, guys? Any questions? That's your default. Unless you know otherwise, you always default to uncoated copper. They used to coat the copper in the past to protect it from the elements. They don't do it anymore unless they tell you it's coated. Does that make sense? But don't forget solid and stranded, because the guys up to, what is it, number 10, I think, they have solid and stranded, or did they go to 8? Number, yeah, table 8. 8. They have solid 8. Yeah. After that's everything stranded. All right. This was seen on the test. We have an 80 amp load. An 80 amp load right here. The voltage is 80 amp. The voltage is 480. It's 3-phase. It's wired with number 4 copper. Can you guys see that? One section. The load is located 110 feet away from the panel, like you see it right here. How far can the load be relocated from the panel and still meet the NEC code book requirement, a recommendation? The load will be reconnected using, because we're knuckleheads, we're using number three aluminum. Does that make sense? Here's the first thing you need to do, guys. Do you see that section here? Look at this. From here to here, this is one problem. This is your problem number 1. Find the voltage drop right here. You need to find voltage drop. Once you find the voltage drop right here, then you start from this point all the way to this point here. You find the distance, right? Because you're going to take the voltage drop that you found here, you take the 3%, subtract the voltage drop that you got, and use it as a leftover voltage drop to find the voltage drop here. Once you get the voltage drop, you know how much extra voltage drop you can lose. Give you 2% voltage drop. Okay, the first, does everybody understand what we're doing? We're doing two problems, right? Everybody understand it? We're doing two. Okay, so let's go find the voltage drop at the original location. At the original location, gentlemen, here's your three pairs, so you need to find R, of course. Here's your R for number, they're uncoded. We found R for copper, and also don't forget that there's also aluminum, an R for aluminum. And there are two sizes. You need to go to the table to find the R for the two cables. Okay, once you find the R, then the voltage drop at 110 feet away from the panel, piece of cake. Here's your 1.732. Here's your 0.308 voltage drop, or I'm sorry, impedance. 80 the amp, the length is 100, so you have this amount of voltage drop. At the current location, we lost 4.69 voltage drop. Okay, doesn't tell me anything. How much a circuit? How much are you allowed to lose on a 480 volt system? You can lose up to 14. Now subtract the 14.4 from the 4.69. Now I'm left over. What's my leftover? I lost 4.69. I'm allowed to lose overall. Gives me an amount of 9.1. Look what happened next. Now you take, now you find the length. Can you can see here's my length? Flip the formula. Then you take, can you guys see this number? That number, you flipped it and put it in the length here, times 100. Here's the new, what do you call this? The new impedance for aluminum. That will get you how many feet? 173.89. Now the question, that's how far you can go from the original location. But the question is, how far can you go from the panel itself? How far you can go from the panel itself? What would it has to be? 283.89 feet. Yep, that was seen on the test. Did they give you the K? Mm-hmm. Why would you volunteer to use the circular mill? You need the K. So you, I bet you assumed 12 point. Yeah. Unless they give you the K, must use the R. Close. Yeah. Well, the problem is these are multiple choice. So it depends how they put the multiple choice. Now your answer will be 283 or 284. It should be 283, right? Can't go further than that. Okay. All right. That's it about voltage drop. That's all we're here about. So let's go talk a little bit, guys, about um, a couple of load calculation. Yeah. So you need to know that. Their tables must know, guys. We'll go over these tables and make sure every table that we go over, make sure you highlight it and know how to use it. Let's start with electric dryers. If you have an electric dryer, we use them all the time. Hotels and motels. If you have hotels, not hotels, apartment buildings. We have an apartment building, guys, and these are household electric, not gas dryers. Okay, if you have 11 apartments, and you're sizing the feeder that feeds all the 11 apartments, all of them, then your derating factor is 47. How do you use it? Okay, no problem. The Nisikot book guy says for every dryer you shall use the following: 5,000 volt amp or the nameplate, whichever is larger. So if your nameplate is 6,000, use 6,000. If your nameplate is 4,000, use 5,000. Am I making sense? 5 or the nameplate, whichever is larger. Okay, suppose that this is a 5, so there's 11 of them multiplied by 5,000 because each one of them is defaulted to 5,000. And that's how you find the contribution of the driver. For the service that feeds these apartments. Am I making sense? Don't forget the 5,000. Now, what happens if your number is 20 here? Then you have to do funky math, right? Let's do this funky math. It says 47. I'm not gonna put the percentage minus one percentage for every dryer, each dryer exceeding 11. So 20 minus 11. Okay. So if we have you question my judgment after the 4 o'clock with the numbers. 38 is it? 38%. Okay, now once I get the 38%, then multiply this by the 20 units that you have. Suppose they were nameplate 6,000. Okay, then you multiply everything by 6,000 and you're done. And that would be the size of the feeder that feeds all these dryers. Obviously, it's not going to feed the dryers by themselves. It's going to feed the whole unit. Okay, there are 22 dryers. Speak of the devil. 22 dryers installed in a multi-family dwelling. Each one of them is 4,500 kVA. Calculate the load demand for feeders and service calculation. Okay, remember the 22. I have 4,500. So would I use 4,500 or 5,000? 5,000. Okay, there we go. For 22 dwellers, gentlemen, 47 minus 1 times 22. Remember that 22 minus 11? That formula that we just looked at? That'll give me 36. Everybody understand how we did this fuzzy math? One percentage for every dryer exceeding 11. So 22 minus 11 times 1, that gets you 11. 11 minus 47. 47 minus 11 give you 36. You have to use the 5,000. So 22 times 5,000 give you this amount. Now then you cut it by this value, and that's what you get. Can you imagine the difference between sizing? Go to the ranges. How are you guys doing with the ranges? Good, bad, or ugly? In between. Okay. Electric ranges. Electric ranges, they have a couple of notes, guys. Let's talk about the electric ranges and how to use the table. All right, so let's go to the notes at the bottom of the table, 1 through 4. That's very important to be used. Okay, column A. If you, when would you, okay, this is default. First of all, your default must be always column C. Always. For example, I have, oh, by the way, when would you use this table? You use this table not for Perkins and McDonald's and all these fast food restaurants or non-fast food. You use it for dwellings, apartments, and single multi-family dwellings only. For the ranges and wall-mounted ovens and counter-mounted cooking units, anything related to the cooking. Okay, so suppose I have 15 apartments and each one of them has a range. The demand for 15 apartments is 30 from the get-go. 15 ranges, the demand is 30. Default is always. Are any of my ranges under A, size-wise? Are any one of them is less than 3 and 1.5? If the answer is yes, then you're going to come and apply the demand factor to that number, to these ranges which are under A. The second question you're going to ask yourself, are any of my 15 ranges within the range of B? If your answer is yes, so what do? You apply B to that column, to all the ranges that go under B. Okay? So there, now we're under B. And then you add these two together. Okay? Add them up. And then you compare the answer with what you got under C. Above 12 there. What happened if you get above 12? Then you have to go note number 1. Can you guys see note number 1 on the table? It says equal sizes ranges with nameplate greater than 12 kW. Okay. If they're all the same size, then you use, say, more than 12. So all of them are 16. How far is 16 from 12? That's not number 1. Not number 2, Joe. I will give you the demand for all these. So this is not number 2. Note number four. Note number four, guys. This is a branch circuit. You use it to size a branch circuit for. Note number four say yes. You can use it for all ranges or for a branch circuit for one counter cooking unit. Suppose I have a range, one range. Now, since the now is the 13 more than 12? So that's for the branch circuit. The last note, guys, which is not number. So instructional programs, um, instructional program for you. If they tell you guys there are 20 ranges in an. Okay, there's some fuzzy math here that you have to do. Can you guys see that? Like within this range here, you have to start doing this math. So 25 kW plus 3/4 kW for each range more than for each range. So suppose we have 40, 40, oops, 40, no. Suppose it has to be within that range. 42. So then you multiply this number by 42. So it becomes 25 kW plus 3/4 times 42. Makes sense? For each range. Okay, here's the notes that we talked about, German. Okay, there are 5 ranges with a nameplate rating of 11 kW. From the get-go, 5 ranges. They're under C, so they have to under C. All of them are under C, so the demand for 5 ranges is 20 kW. Ask yourself the question: is any one of them under A or B? Look at their size. They're 11. Okay. Is any one of them more than 12? You're done. That's it. It can't be better than that. You're not under A, you're not under B, and none of them is more than 12. You're done. That's it. Let's look at this guy. Where there are 6 ranges with a nameplate rating of 15.6 kW each. What is the feeder? So this is column C, note number 1. Is any one of them, guys, under A or B? No. So they're under C. So then you have to go. Um, so how far? They're 15.6. 15.6 will turn you round up to 16. How far is 16 from 12? 4. So for every kW increase 5%. So that will get you, and then you increase your demand for 5 ranges, 1.25. Don't up. What if that was 15.4? Where do you go? Down. No, 15.4 down. 15.5 up. Point 0.5 is the cutoff. 0.5 down. Okay, cool. All right. My question for you is: any one of them under C, and which note applies to them? They're different. Note number two. Number two. Okay, if you look at note number two, gentlemen, it says they're all different sizes. None of them is under A or B. You add them up. Less than five, make it 12. That's the when you apply note number two, gentlemen. They're all different sizes. None of them is under A or B. They're all under C. Different sizes. But I think 12 make it 12. Did you guys hear me? I didn't say 12. 12. Okay. Then average them. How do you average them? Divided by the number. 15.4. 15.4 down into 1. Then then how far is 15? So 15.4 round down, right? Then 15 is 3 kW from 12. That'll get you an increase of what? 13%, 15%. And what number 12, average them, and in more than 12. Okay, gentlemen, I have another one. From the get go. Can you guys give me the minute for 4 under C, please? 17. Okay, for 4 of them under C, 17. Okay, hold your horses though. Then you're going to ask yourself, some of them are under A, some of them are under B. But okay, perfect. Very good, gentlemen. So there was one of them under A, so that'll give you 80% derating factor. And the rest of them are under B. That'll give me three of them. Three of them. The rating for three is 55%. After you derate them, add them up and multiply by 55. That will give you this number. Then don't forget to add the two together, right? These. Add the two together. That will give you the total. And then compare them. Then compare them with what? So which number? Under C we got 17. Under A and B we got 4.85. Which one are you going to use? The lowest, 4.85. Any comments guys about ranges? Any comments, questions about ranges? So my last question, guys, for the day before I let you lose here. Um, up face value. These are non-dwelling gentlemen. Add them up. You apply. So if you have 6 of them or over, associated with the. Okay, so look at these pieces of equipment, please. So I have grill, deep fryer, oven, dishwasher, heater, ready, infrared, processor, 2 microwave. Oops, how about this chunk here? HVAC, rooftop unit. Is that directly related to the preparing of the food? Okay, and they're asking about the feeder demand for this commercial kitchen. What's the feeder demand for this commercial kitchen? Okay, you're gonna add all just the equipment, guys. Add them all up, and so don't add the HVAC. At the end, we'll add the HVAC. Everybody can see that. Okay, how many pieces of equipment do I have? 9 of them, 8 of them. For 8, what's my demand factor? 65. Add them all up. There you go. So add them all up. Remember, there was 2 microwaves or something. Here's your total. Then cut them by 65 is your demanded. Can you just see how it cuts it way too down, right? Otherwise, the equipment will be huge. So that would be 83.2 kW. That's only for the equipment, gentlemen. That's only for the cooking equipment, directly related to the cooking, right? Now, once you do that, what do you need to do next? We need to look at the largest pieces of equipment. The code says you have to look at the largest piece, add them up, and make sure you're not lower than the 2 largest equipment. So one more time. All right. Once we have a feeder that feeds. Any comments, guys? Any questions about that? One more if you guys good. For a new single. Okay. So 100 amp. So here's your 100 amp. That's a service is 100 amp. In 2014, guys, there used to be a nice table. Oh, by the way, you know what happening to that table? It's coming now in 2017. In 2017, and they're putting it in the D, Annex D. They're not changing the rule, but they're putting it in 2017. Anyway, if you guys go there, it says if you're doing a single family dwelling, multiply by 83%. So take your service, they'll get you 83%. And then from 83%, then you go to 310 or 15B17. Oh, by the way, I'm doing 75-degree. That's not true. So they'll give you number 4. By the way, It's coming. What it could be, yes. Fuses and breakers, yes.